Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into section 4.3 from your textbook, which introduces you guys to the idea of a subspace. Now, in the previous set of videos, we introduced and did a very thorough discussion of the concept of a vector space. And we saw that a vector space was a mathematical structure that satisfied a list of 10 axioms. And those axioms could have been divided into some major groups. There were closure axioms, there were axioms about the properties of vector addition, there were axioms about the properties of scalar multiplication, and there were some axioms about how vector addition and scalar multiplication would interact through distributive properties. And we saw that if you defined a set of vectors and a set of scalars and a vector addition and scalar multiplication operation that satisfied those 10 axioms, then what you would build was a vector space. And a vector space was something that acted like the vector spaces that you guys had studied in geometry and in multivariable calculus. But we had generalized that concept to get to the underlying structure. In this video, we're going to be continuing our study of vector spaces, and we're going to focus on a very important idea inside of vector spaces, literally inside, because we're going to be talking about subspaces. Subspaces are basically vector spaces that live inside of other vector spaces. And the reason that this is so important is that if we're working inside of a thing that we know already is a vector space, and remember in one of the section 4.2 videos, we talked about some very important standard vector spaces like Rn, Cn, the polynomial vector space, the matrix vector space, and the vector space of either continuous or differentiable functions. If we know we're working inside one of those, then checking whether or not something is a vector space, if it happens to live in one of those, actually is tremendously easier. And that's the concept of a subspace. So let's go ahead and get some formal definitions and then start taking a look at some examples. So we're going to start talking about subspaces. So first, a definition here. So let's let S be a non-empty, so it's got to have some stuff in it at least, right? So let S be a non-empty subset of a vector space V. So we have a vector space V, and we've got this subset S inside of it. So if S is also a vector space under the same operations, vector addition and scalar multiplication, defined for V, then S is said to be a subspace of V. So S being a subset just means that the elements that are in S are also elements of V. But being a subspace means that S by itself also satisfies the 10 axioms of being a vector space. So basically what you can think about is that S, a subspace, is a vector space that happens to live inside of a larger vector space. Now, the very first thing we're going to do here before we get into some examples is prove a very important theorem about subspaces. This theorem basically tells us that when you need to check if something is a subspace, it is actually much easier to check if it is a subspace than it is to check the 10 axioms of being a vector space. In other words, there's only a couple axioms that we actually need to check. The other ones are guaranteed to be true. So let's take a look at this theorem and we'll prove it. So this theorem says let S be a non-empty subset of a vector space V. So we've got our big vector space V, and we have S a subset of it. Then S is a subspace if and only if S is closed under vector addition and scalar multiplication. So what this says, right, and once we've proven it, what this allows us to do is say, if we know that S lives inside of something that is a vector space, then to check that S is a subspace, you do not need to confirm all 10 properties. You only need to confirm 2 of them. You just need to confirm that it's closed under vector addition, and you need to confirm that it is closed under scalar multiplication. In other words, those first 2 axioms, the 2 closure properties, are the only ones you need to check if you know that the thing you're studying lives inside of a larger vector space. So let's go ahead and prove this. As a proof, right, this is an if and only if statement, so there are going to be 2 directions. One of them is going to be absurdly easy, and we'll do that one first. So we're going to go this way, right? So what we need to show is if S is a subspace, then S is closed under the addition operation, whatever it is, and the scalar multiplication operation. Well, this is going to be a ridiculous easy thing to show, because if S is a subspace, what does that mean? Well, being a subspace is this definition here. That means it is a vector space. What do we know about vector spaces? Well, they are closed under vector addition and scalar multiplication. So this is a very easy proof. S is a subspace implies S is a vector space, and vector spaces are closed under vector addition and scalar multiplication. Check. Okay. That is the very boring direction of the proof. That doesn't really tell us anything, because that's saying if we already know it's a subspace, then these things are true. Okay, but that's not how we want to use this theorem. We want to use this theorem to say if we can show these two things, then we know it's a subspace. So let's do the more interesting direction of the proof. So now we're going to do this direction. What we need to show is if S is closed under these two operations, then it's a subspace. So we need to show that if it just is closed under vector addition and scalar multiplication, then it is automatically a subspace. And again, being a subspace means that it is a vector space, right? So to do this, need to verify P1 through P10. We need to go through and do those 10 axioms or those 10 properties. Now, if you watch the last 4 videos walking through section 4.2, we went through and worked a lot with those 10 properties. We probably don't want to have to go through one by one and do them all over again in this situation. Luckily, we don't have to. A lot of them we get for free. Since, right, S is a subset of V, which is a vector space under plus and the scalar multiplication, we know that, well, what do we get to know for free? Well, we know that S is inside of V and it has these two operations. So we know these two operations satisfy all the properties that relate to them being appropriate vector space properties. So we know things like property 3, which is that this guy is commutative, will be true. We know P4, that this guy being associative will be true. We know things like the unit property, P7, for scalar multiplication will be true. We know that P8, the property of associativity of scalar multiplication will be true. And we know that the distributive properties, P9, P10, all will be true. Okay? We know all of those are true because these guys don't relate to vectors or what is or is not in the subspace. These just relate to the operations of addition and multiplication, and we know that those operations, when we're working with V, act the way that they're supposed to. So we know that those all will be true. By assumption, we know P1, P2 are true. Right? P1 and P2 are the operations that deal with closure, and we're assuming in this direction of the proof that this space is closed under vector addition and scalar multiplication. So P1 and P2 are done. So a quick check: P1, P2, P3, P4, P7, P8, P9, P10, all of those are guaranteed to already be true. That leaves only 2 that we need to confirm. P5, the existence of the zero vector, and P6, the existence of additive inverses. Those ones we need to confirm. Now you might ask yourself, why do we need to confirm those? Why can't we just say, well, we know the zero vector is in V, and we know that additive inverses are in V because V is a vector space. Well, that's true. We do know that the zero vector is in V, and we do know that additive inverses are in V. But we need to know, is the zero vector going to be in S, and are additive inverses for all elements in S going to be in S? Because remember, we're trying to show that S is a subspace. We know V is a vector space. We need to show that S is a vector space. So let's go ahead and do that. P5, zero vector. Well, recall, right, that 0 as a scalar dotted with any vector V is going to be the zero vector, right? This is one of those additional properties we showed. We said that in a vector space, right, if you take the scalar 0 and scalar multiply with any vector v, you're guaranteed to get the 0 vector. Well, let's let v be an S, then this 0 vector must be an S, since the S is closed under scalar multiplication. So we're just doing a little trick here. What we're doing is we're saying, okay, let's pick out a vector that we know is in S. It's got to have something in here. Why do we know that there's got to be something in S? Well, because S is non-empty. Then we're saying that that guarantees that the 0 vector is in there. Because if we do 0 times whatever vector we choose from S, that gives us the 0 vector, and we know S is closed under scalar multiplication according to this here. Okay, we're going to do the same trick for P6, right? Additive inverse. Okay, we're going to recall that one of the additional properties we showed is that -1 is a scalar. Scalar multiplied with a vector v gives its additive inverse. So let's let v be an element of S. Then, well, we just know -1 or negative v being -1 scalar multiplied with v is an element S. It's an element of S since S is closed under scalar multiplication. So that shows us that the 0 vector and all the additive inverses of any vector inside of S are guaranteed to also be in S, since S is closed under this scalar multiplication. So S is a vector space, which implies S is a subspace, because we've already assumed that S is inside of V, so showing that S is a vector space makes S a subspace. And that's what we wanted to show here. So what this theorem sort of tells us overall is that if you need to check whether or not something is a subspace, all you need to confirm is that it is closed under vector addition and scalar multiplication. So let's go ahead now and take a look at a couple examples of using this theorem and checking whether or not different sets are going to be subspaces of some pretty important vector spaces. Before we do that, though, we're going to make one quick mention of a little corollary to this theorem that can also be used for very quickly ruling out certain things as subspaces. So let's go ahead and talk about that real quick. So this is just called, this is just a note, 0 vector check. As a follow-up to the previous theorem, keep in mind that if the 0 vector is not an element of S, then S is not a subspace. So this is a very sort of important quick check. If you're ever asked whether or not something is a subspace, first thing you should always do is think about whether or not the 0 vector is in there. If the 0 vector isn't in the subspace, then it's automatically not a subspace. How do we know that? Well, if the 0 vector is not in there, then it's going to fail that property. What happens if the 0 vector is in your thing that you're looking at as a subspace? Well, then this 0 vector check doesn't give any information. So if the 0 vector is in there, then you need to continue to study that space and determine whether or not it really is a subspace. If the 0 vector is not in there, then you're already done. You know it is not a subspace. So now let's go ahead and take a look at some examples. So our first example here, we're going to try to determine if the following set is a subspace of the given vector space. So our set S, which may or may not be a subspace, is as follows. It's the matrices that are elements of M3, so 3 by 3 square matrices that have the property that the determinant of A is equal to 0. And we want to know whether or not that set inside of the space of matrices that are 3 by 3 square matrices, is that a subspace? Now, as we get more and more practice with this, we can go faster and faster, but let's just do a couple things first. Let's just do a couple checks. Typical, or let's not say typical, let's say examples of elements in S. Let's just see if we can put together some examples of things that are in here, right? I mean, we could try to just jump in and work on this, but let's just see if we can think of things that are actually examples of things in S. So what are things in S here? Well, they need to be 3 by 3 square matrices, and they need to have this property that the determinant is 0. So you could have something like this. 0, 0, 0, 0, 0, 0, 0, 0, 0. The zero matrix, right? The zero matrix is, the 0 3 by 3 matrix is certainly a 3 by 3 square matrix, and it certainly has determinant 0. You could also have something like this. We know something that like 1, 0, 0, 0, 0, 0, 0, 0, 0 would be in there. Why do we know that's in there? Well, because we know that something that like this that's diagonal, well, the determinant is just the product of the diagonal elements. We know that something like this, something like 0, 0, 0, 1, 1, 1, 1, let's go back and say 0, 1, 1, 1, something like that. Well, this guy is lower triangular, so we know that lower triangular matrices, their determinant is the product of their diagonal elements, which is going to be 0 though. Or you could even have something like this. If you really think back to what we know about determinants, we could have something like 1, 2, 1, 2, 4, 2, maybe 3, 5, 8. Who cares, right? The reason I know that this guy has determinant 0 because we know that this guy here is a scalar multiple of this row here. So you could use an elementary row operation to zero out this row. And then we know that once something has a 0 row, it's guaranteed to have a determinant of 0. So all of these things are elements in S. Now, just because we wrote these down doesn't mean that S is a subspace. This is just what it means to be a subset. These are all examples of matrices that would be in this set. The question is, if we use the standard operations of matrix addition and scalar multiplication, is that going to mess up and make us leave this set? In other words, is it not going to be closed under those operations? All right, so let's do our zero vector check real quick. Well, what's the zero vector in the space of matrices? It's just the zero matrix, and we just showed that that's there. So the zero matrix, 0, 0, 0, 0, 0, 0, 0, 0, 0, is going to be an element of S. So what does that tell us? Well, nothing. That tells us the zero vector is in there, so this thing could be a subspace. Doesn't tell us that it is a subspace, doesn't tell us that it isn't. This, in other words, this zero vector check actually sort of failed because the zero vector is in there, so we don't get any information. So no info. All right, so let's now think a little bit about like closure under addition and scalar multiplication. So if we know that the determinant of one of these elements is 0, do we know then that the determinant of the sum of two of these matrices is going to be 0? In other words, let's talk about closure under addition here, right? If A and B are elements of S, then is A plus B going to be an element of S? In other words, is the determinant, we don't really need the fancy plus here because we're just using our standard operations. Let's not confuse ourselves. Let's say, then is A plus B an element of S? In other words, if we know that these guys are going to have determinant 0, can it be guaranteed that this guy is going to have the determinant 0? Well, this would be true if we knew that determinants distributed over addition. But if you think back to when we learned about determinants, we never said that they distribute over addition. We said that they distribute over multiplication. So we should be a little suspicious of this. And actually, if you look at the sort of examples I wrote, you can actually see a counterexample right away. If we consider right here, we can see, note, 1, 0, 0, 0, 0, 0, 0, 0, 0 is an element of S, and 0, 0, 0, 1, 1, 0, 1, 1, 1 is an element of S. But if we add these things, 1, 0, 0, 0, 0, 0, 0, 0, 0, plus 0, 0, 0, 1, 1, 0, 1, 1, 1, what do we get? We get 1, 0, 0, 1, 1, 0, and 1, 1, 1. Well, what do we know about this guy here? Well, this guy is lower triangular, but the determinant here, right, the determinant of this, let's write it out more nicely. but determinant 1, 0, 0, 1, 1, 0, 1, 1, 1 is equal to 1, which is not 0. So what does that tell us? This guy here is not an element of S. So this shows us that even though we took two things that were in S and we added them together, we got something that's not inside of S. So S is not closed under, well, we don't need the fancy notation because we're just using the standard operation, under plus, so it is not a subspace. So when you show something is not a subspace, all you need to do is give a single example of what violates either the closure under addition or the closure under scalar multiplication. Interestingly enough, if you guys want on your own, you can show that closure under scalar multiplication actually is true. If you start with a matrix that has determinant 0 and you multiply it by a scalar, you will still have a matrix with determinant 0. So scalar multiplication is not the problem. It is the vector addition, or in this case, the matrix addition, that is a problem. So our first example here, while an interesting subset of it, the space of 3 by 3 matrices, it is not a subspace. Okay, let's take a look at another one. All right, so we've got this guy, which is going to be the set of functions that have the property that their first derivative evaluated at 0 is equal to 0. And these functions come from the space of functions who have an infinite amount of derivatives defined on all real numbers. And we're working inside that vector space of all functions that have an infinite amount of derivatives over all real numbers. So let's again sort of just think about some example elements. So what are some things that live inside of this? Well, we need to think of functions that have this property, that have a derivative at 0 equal to 0. So I could maybe think of something like f of x equals 0. The 0 function. If I take the derivative of that guy, I get 0, and then if I evaluate it at 0, I'll get 0. You could have something like f of x equals 5. That's a constant function. If I take the derivative of that, I get 0. I plug in 0, I will get 0. We could think of something like maybe f of x equals cosine x. You take cosine x, you take its derivative, you get negative sine x. You plug in 0, you get 0. So all of these things would be examples of things that live inside this space. Could you think of more complicated ones? You know, sure, right? We could play around and probably realize that something like x cubed plus 10x squared is also an element. How do I know that? Take its derivative, 3x squared plus 20x, plug in 0. Well, there's an x in every term. It's going to be 0. That guy's in there. So all of these would be example elements inside this subset. Okay. Now let's do that 0 vector check. Well, what is the 0 vector in this space? Well, it's the 0 function, and we already realized it's in there. Right? F of x equals 0 is an element of S. Check. So, again, no info from the 0 vector check. But again, remember, if this guy was not in there, we'd already be done. We'd already be able to say it's not a subspace and get to move on. So it is always worth doing this 0 vector check right at the beginning. All right, now let's consider closure under addition. Well, I don't necessarily know if it's obvious whether or not it's going to be closed under addition. It's sort of asking, do you think that the derivative of two functions that both have the derivative 0 being 0 is still going to have a derivative that is 0 at 0? So let's proceed as if it's true, try to prove it, and see what happens along the way. So let's let f of x and g of x be elements of S. We need to show that f of x plus g of x is an element of is an element of S. Excuse me. All right. So what do we need to show then? Well, we need to show that f of x plus g of x is an element of S. To be an element of S, you have to have this property that your derivative at 0 is 0. So what we need to show is we need to show that f of x plus g of x prime evaluated at 0 is 0. So we need to show that the derivative of this, evaluated at 0, is going to be 0. So let's try to do that. F of x plus g of x prime at 0. Well, we know that derivatives distribute over addition, so that's a good sign. That means we can say that that's f of x prime, g of x prime, evaluated at 0. And that's f prime of 0 plus g prime of 0. Okay, well, what do we know about f prime of 0 plus g prime of 0? Well, f prime of 0 has to be 0 because f is an element of S, and g prime of 0 has to be 0 because g is an element of S. So this is 0 plus 0, since f, g are elements of S, and that's 0. Check. So we've just shown that if you start with two functions that are inside of S, then when you add them, you will remain inside of S. So in other words, it is closed under addition. Let's try the same thing with closure under scalar multi. So let's let f of x be an element of S and k just a real number. We need to show that kf of x is an element of S. So we need to show that if we take kf of x and take its derivative and then evaluate at 0, that we're going to get 0. So let's go ahead and actually try to work left-hand side to right-hand side and see what we get. So kf of x prime at 0. What can we say about that? Well, what do derivatives do over constant or scalar multiplication? We know that they distribute through. So that's the same as kf prime of x evaluated at 0. And again, I'm just using notation like this as evaluated of 0. It's a little bit of poor notation. I guess we could just jump to make it a little bit clearer. Let's just jump and go ahead and pop it in there. That would be kf prime at 0, because of course there's no variable in k, so you know that the 0 is just going to plug into the x. And then what can we say about this? Well, f of x is an element of S, so that means it has this property. So that means it's k times 0, which is 0. So we did it. So we just showed, right, that it is closed under addition, it is closed under scalar multiplication. All other 8 properties come for free because we know we're working in this vector space. So we now know S is a subspace. So we've just shown that this set of functions is a subspace. And if you want to, for fun, what you can do is you can go back to some of our examples and you can sort of check that if you take this function and you add it to this guy, you still have something that satisfies this property. If you take this guy and add it to this guy, you still have something that's in this set. If you take this and you multiply by 7, you'll still have something that's in this set. You take this guy and you multiply by -1,000,000, you'll still have something in this, because we've proved that it is closed under addition and closed under scalar multiplication. All right, let's take a look at another. All right, so we're going to try this guy. We're going to try to determine if the following set is a subspace, again, of the given vector space. So we have the set S here, which is made up of these 4 tuples that are of the form a squared, b, 0. And these guys live, of course, inside R4, which is the space of all 4 tuples. So let's look at some example elements. What are some example elements here? Well, something like 2, 4, 3, 0. That would be an element. That's choosing A to be 2. That makes A squared 4. That makes B 3. And we just choose B to be 3 and then 0. You could have something like -5. Then this guy has to be 25. Then you can put anything you want for B. So maybe we put 7 and then 0. You could have something like A is 0, A squared then has to be 0, B could be 0, and then the last guy has to be 0. You could have something really weird like -1, and then 1, and then B could be 17, and then you'd have 0, right? All of those are example elements, right? That's what this sort of set is made up of, things that look like this. Okay. Let's do our 0 vector check, although I already technically did it. Oh, my apologies there. Don't quite know what happened. So let's go ahead and do our 0 vector check. All right. Well, is the 0 vector. Well, what is the 0 vector in R4? It's just 0, 0, 0, 0. We just talked about how that's in S, so 0, 0, 0, 0 is an element of S. Check. So again, no info. Okay, so the 0 vector is in there. Again, one of the reasons I do want you guys to think about that 0 vector is also, if you look over these examples that we've been doing, the 0 vector that we've been looking at each time has been very different, right? The 0 vector in our first one here was the 0 matrix because we were working in M3 of R. In this guy, the 0 vector, again, 0 vector in quotation marks, but terminology we're applying in general, was the function f of x equals 0. And the 0 vector this time is literally a 4-dimensional 0 vector because we're inside of R4. Okay, let's think about closure under addition. So, again, maybe we don't know if it's going to be true or not. We can sort of look up at these examples and think about, well, if I add these guys, do we think that it's going to remain in here? And I'd be a little suspicious, right? I'd be a little suspicious about this a squared. If you think about just adding these two, well, if I add 2 and -5, that's going to give me -3. And then according to that, that means the second component had better be -3 squared, which is going to be 9. But we're going to add 4 and 25, and that's going to make 29. Those aren't going to be the same. That tells us this thing's not closed under addition. So let's go ahead and actually see that. So just note 2, 4, 3, 0. And -5, 25, 7, 0 are both elements of S. I mean, that's what we did right here. We're just talking about things that we know are elements of S. But 2, 4, 3, 0 plus -5, 25, 7, 0, which would be -3, 29, 10, 0, is not an element of S because 29 does not equal -3 squared, right? This restriction that the first component can be anything, but the second component has to be its squared is not going to be satisfied. So this guy fails under closure, under addition. So S is not a subspace. Done. Now, this guy is technically done, but just for fun, I also want to show you guys that unlike the first one, this guy actually does fail under scalar multiplication too. So we'll just do this as a side note. Side note. Also fails scalar multi closure. We can actually use this same element here. Let's just multiply it by like, I don't know, maybe like 3 or something. So 3 times 2, 4, 3, 0 would be something like 6, 12, 9, 0. But this guy would not be an element of S. Again, because this guy here, who's supposed to be this guy's square, well, he wouldn't be, right? Because 12 does not equal 6 squared. So this guy would also fail under scalar multiplication, because if you multiply one of the vectors inside this space with a scalar multiple, you don't get something that still is inside the space. So you leave the space when you leave the set when multiplying by a scalar. That means it's not a subspace. Okay, let's take a look at another. All right, so we've got this guy here, right? We want to take a look at this set, which are functions that have the property that at 0, they are equal to 2. And these functions come from the space of F0 of R. Remember, this just means the space of functions that are continuous, right? Don't have to have any derivatives, 0 derivatives necessary. They can have derivatives, but they don't need to. That are at least continuous over all real numbers. Okay, so what are example elements here? Well, you could have something like f of x equals 2, right? If I plug in 0, I will get 2. Something like f of x equals x plus 2, right? I plug in 0, I get out 2. You could have something like f of x equals x squared plus 5x plus 2. Plug in 0, those will 0 out, and you'll get 2. You could have something like, how about cosine x plus 1. Plug in 0, that'll be 1, plus 1, that'll be 2, so that guy's in there. All of these are examples. Okay, let's do our 0 vector check. Hasn't really yielded anything thus far, but let's go ahead and do it. 0 vector check. Okay, What is the zero vector that we're looking for? Well, we're working in the functions that are continuous on all real numbers. So f of x equals 0. Is this function in this set? Well, f of x equals 0. You evaluate that at 0, you get 0, which is not 2. So this guy is not an element of S, since f of 0 is 0, not equal to 2. So this 0 function, which acts as the 0 vector, is not inside this space. So what does that tell us? S is not a subspace. So we're done. That's all we need to do. So this again is a big sort of motivator for why the zero vector check is worth doing. When it works, like it did here, where we saw that the 0 function, which acts as the 0 vector, was not inside of S, we're done. It's already not a subspace. Okay, we've got just a couple more to take a look at here. Let's go ahead and look at this guy. So again, staying in the space of functions. So now we're going to look at the set of functions who have the property that their derivative at 0 is equal to 0. And these functions are going to come from the space of functions that have an infinite amount of derivatives over all real numbers. So let's again look at some example elements here. So what are some example elements? Well, we can think of, we've got things like, oh, my apologies. I think this is the same example. Is it not that we already did here? Oh. Well, we already did this guy, so we don't need to talk about that. We can go on to the next one. There must be just a copy over error. Sorry about that. Let's go ahead and continue on. We got this guy here. Yep, there we go. So we want to take a look at this guy, which is, we want to take a look at something inside the space of matrices. We've got this set that are matrices that have the property that their sum, remember the sum is just adding up all of their elements, that their sum is 0. And these guys come from the space of matrices that are 3 by 2 inside of the standard space of 3 by 2 matrices. So let's go ahead and look at some example elements here. So what would be examples in here? Well, they'd have to be 3 by 2 matrices. So 3 rows, 2 columns, and they have to have a sum that is 0. Well, I could do something really dumb like 1 minus 1, 2 minus 2, 3 minus 3. Right? That'll work because when I add all those up, 1 plus minus 1 plus 2 plus minus 2 plus 3 plus minus 3, it's going to be 0. You could think of something a little less dumb, maybe a little more interesting. 1, 3, 2, 1, 1. Well, once I've done that, what do I have? I have 1, 4, 6, 7, 8. So I better put a minus 8 there. And then I know that the sum will be 0. Obviously something like 0, 0, 0, 0, 0, 0 will work. All those are example elements. Why did I bother mentioning this guy? Well, that would be the zero vector check. Actually, right? Zero vector here is going to be this guy, 0, 0, 0, 0, 0, 0, which we just showed is an element of S, check, so no info. But at least we talked about it, right? This time, zero vector check didn't give us anything. Okay, now we got to sort of ask ourselves, if we were to add things like this, or if we were to scalar multiply one of these, are we going to get something that also has a sum that is 0? Well, it's going to be maybe sort of tough to show that because sum is not something that we did a lot of properties of. So maybe before we get into talking about trying to show whether or not this is closed under addition and scalar multiplication, let's think a little bit more about what this set actually means, sort of like how we constructed these. So let's actually talk about a general element of S. So let's think about what these guys need to look like. Well, you can sort of put anything you like in most of the spots. If you think about how I built this example, I just put random numbers in all 5 of these spots and then made this guy the exact thing that would guarantee the sum is 0. So you can sort of think about this general element as having a bunch of free parameters. You can put anything you like there, anything you like there, anything you like, anything you like, anything you like. But once you've selected those 5, you have to pick out exactly the sum of all these elements negated. So this last guy would be negative a plus b plus c plus d plus e. And that would be a choice we wouldn't get to make because that would guarantee that the sum would be 0. Okay, now why did I spend time to talk about that? Well, by knowing this, it'll be easier to look at the properties of closure under addition and scalar multiplication. So let's let A1 and A2 be elements of S. We need to show that A1 plus A2 is an element of S. So A1 plus A2, what does that look like? Well, let's call A1 of this form all with subscript 1, and A2, this form, all with subscript 2. So let's call that A1, B1, C1, D1, E1, and then negative A1 plus B1 plus C1 plus D1 plus E1. And then A2 would look the same, except everything just would be 2s. A2, B2, C2, D2, E2. And negative A2 plus B2 plus C2 plus D2 plus E2. Okay. And what would happen when we add those? Well, looks like we would get something like A1 plus A2, B1 plus B2, C1 plus C2, D1 plus D2, E1 plus E2, and, well, oh, my apologies over here, that negative's out of place. That guy should be negative, and then parentheses, okay? Well, we can add these guys inside of their negative, so we can see that as negative A1 plus A2 plus B1 plus B2 plus C1 plus C2 plus D1 plus D2 plus E1 plus E2. Sort of horrendous looking, but if you think about it, what's in here is just the sum of all these guys, so this guy is certainly going to have sum 0. In other words, this is an element of S. So we've shown that it is closed. So S is closed under addition. So we've shown that it has that closure property under addition. Let's try the same thing for scalar multiplication. So need to show if A1 is an element of S, K is a real number, then KA1 is an element of S. So KA1, what does that look like? Well, that's K, A1, B1, C1, D1, E1, and then we said negative A1 plus B1 plus C1 plus D1 plus E1. Well, scalar multiplication just distributes onto all elements. So that's going to be KA1, KB1, KC1, KD1, KE1. And when we distribute this, it could go out here, or we could distribute it inside onto every element, which would be negative KA1 plus KB1 plus KC1 plus KD1 plus KE1. So what does that tell us then? Well, that tells us that these guys here are the sum of these. So, since it's negated, the sum of that is going to be 0. So, KA1 is an element of S. Okay. So, S is a subspace. So, this set here, this set of all the 3x2 matrices that have a sum that is exactly 0, is a subspace of the set of all matrices that are 3x2. All right,